Okay, so chapter 13 deals with aldehydes and ketones, and we've already spent some time talking a little bit, or at least mentioning aldehydes and ketones tonight. And we'll start here with the structure and physical properties of aldehydes and ketones. The first thing I'll say is that whenever you have a carbon that is doubly bonded to oxygen like this, we call that a carbonyl group. So that's a carbonyl group.
Hey, Mr. Dion, I don't think any of us can see your screen.
Good?
Yeah, it's good now for me.
Okay, so we call this a carbonyl group. And so carbonyl groups are not only found in aldehydes and ketones, they're found in other functional groups as well. So say, for example, if I was to put this functional group up here, this is an ester, right? And an ester has a carbonyl group in it. Another functional group would be an amide. So if I drew this, this would be a tertiary amide. Anyhow, we can just call it an amide for now. But an amide also has a carbonyl group in it. So an aldehyde is not a carbonyl, a ketone is not a carbonyl, but they both contain a carbonyl. All right, so the carbonyl in an aldehyde, we have an R group on one side and a proton on the other side. And in a ketone, we have R groups on both sides, like that. So you should be fully aware of what an aldehyde and a ketone are and what a carbonyl group is. All right, let's talk about the structure and physical properties of aldehydes and ketones. It says that aldehydes and ketones are polar compounds. Why would that be? Now, I'll just draw an example of a ketone. And so we have our carbonyl group like this. And you should know that oxygen is more electronegative than carbon. And so there's going to be a dipole in the molecule going that way. You see here that in this diagram at the bottom, what they've done is they've taken a ketone, and instead of drawing a dipole with an arrow the way I have, they used the delta symbol. And they said, well, the dipole is pointing towards the oxygen, so that will be partially negative, and that will render the carbon partially positive. And so although an aldehyde or a ketone don't possess the ability for hydrogen bonding, since they are polar compounds, right? It says here aldehydes and ketones both are polar compounds. They experience dipole forces. So these are dipole forces being shown on this slide. And so they have three ketones, and you can see how their carbonyls all align like this. And you can see the dipole forces shown right here, okay? It's not a hydrogen bond, it's a dipole force. It's much weaker than a hydrogen bond, but it's stronger than a London force. And so if you were to have a bottle of acetone, of course, you know, acetone is a ketone, or I should just say any ketone, okay? Well, all of the molecules are going to be tumbling around in space, but they have the ability, to align like this. And that is one of the reasons why aldehydes and ketones have a higher boiling point than alkanes do, or hydrocarbons. Now, I just told you that if you have a pure sample of two aldehydes, okay, two aldehydes or more, there is no hydrogen bonding shown on this slide, okay? So let's get that clear. There is absolutely no hydrogen bonding being shown here, okay? None whatsoever. But if you have an aldehyde or a ketone mixed with something that can hydrogen bond, like water, that's shown here on this slide, then an aldehyde or a ketone can participate, okay? Mark my words, participate in hydrogen bonding. And that's what's going here. You see two ketones, and you also see two molecules of water. There's one here and there's one here. And they're showing the partial negative charge on the oxygen, hydrogen bonding with the partial positive on the hydrogen. And so water, in this case, we call this an H bond, a hydrogen bond donor, because he's the one that's got the electropositive hydrogen, whereas the ketone, we call that a hydrogen bond acceptor, because it's accepting the hydrogen bond from something that is capable of hydrogen bonding. And that's why many small ketones and aldehydes are soluble in water, because of that favorable interaction between the dipole on the carbonyl and its ability to hydrogen bond with something like water. And it says here that water, but it could also be a small alcohol. Anyhow, we'll just stick with water for right now. All right, so what else? Physical properties. This is a classic in Chemistry 102. We love to ask this question right here. We'll give you a bunch of different compounds, and then we say rank them in order of boiling point, going from lowest to highest. And you can see here, we're starting with low boiling point, and we're going all the way up to the highest boiling point out of these 5 compounds. So let's see. We've got an alkane, we've got an ether, okay, we've got an alcohol. Oh, sorry, these aren't in order, are they? I just noticed that. We have an I'll have to delete that. Alcohol, and then we have an 2 aldehydes, or sorry, an aldehyde and a ketone. Sorry, Mr. Dion's off his rocker here. They're not in the correct order, are they? Anyhow, let's take a look here. So when it says carbonyl, it says carbonyls boil at, if you're like, what's a carbonyl? A carbonyl is just a generic way of saying an aldehyde, or a ketone. So if you're talking to another scientist and said, oh, we're studying carbonyls, all that really refers to is aldehydes and ketones. Now, it says here that they boil at higher temperatures than hydrocarbons and ethers, but at lower temperatures than alcohols. And so what I should have done is put these 2 compounds, the aldehyde and the ketone, in some kind of box and put them in between here. Okay. Now we go with the alkane, and the alkane has the weakest intermolecular forces because it only has London forces, nothing else. Okay. All molecules experience London forces. So does the ether, so does the alcohol, so does the aldehyde, so does the ketone. But we're going to evaluate the strongest intermolecular forces of all these compounds. Now, before I proceed, I should note that each one of these compounds has a molar mass that's pretty close, okay? They're all either 58 or 60, so they're all similar in size. So notice that these are all similar in size. Okay, so let's get back to it. We have the ether, which has dipole forces, or dipole forces and London forces, as do the aldehyde and ketone. And if you're wondering, well, how or why would the aldehyde or ketone have a higher boiling point than the ether? You can just memorize that and say, okay, I know that an aldehyde or a ketone will have a higher boiling point than an ether. But the reason why is because the ether, if I draw an ether, if I draw the angle, the bond angle in an ether, that dipole, it definitely exists, right? There's a dipole from the molecule going in this direction overall, okay? But the thing is that dipole is kind of blocked by these 2 R groups over here, so it's not as strong as the dipole in an aldehyde or a ketone where the carbonyl is kind of sticking out like that, okay? That's the rationale as to why ether has a lower boiling point. It's because its dipole force is weaker than that of an aldehyde or a ketone. Now, an alcohol, that's going to be the king of the castle because it is capable of hydrogen bonding, which is the strongest type of intermolecular force that we look at in this class. And so I know that somebody out there is thinking, okay, well, what about on an exam, Mr. Dion? What if you give us an aldehyde or a ketone and you say, you know, which one of these is going to be higher boiling, which one's lower boiling, because they're both very close, 56 and 49. The answer, the final answer is, I don't care what order you put them in, okay? If you put the aldehyde before the ketone or the ketone before the aldehyde, no matter what, you're going to get the correct answer, okay? I'm not going to, you know, ask you to try to differentiate between 2 compounds that are that close in boiling point, okay? So if I ask you a question about ranking compounds in order in terms of their boiling point, it will be something that is abundantly clear, okay? So not something designed to try to trip you up, okay? All right, just like every other chapter in Chemistry 102 that deals with organic chemistry, there's always a big section that deals with nomenclature. And I'll just tell you right now, strap your skates, Gordy, or strap on your skates, Gordy, because this is kind of a big section, okay? Because we're learning how to name both aldehydes and ketones. And not only that, but you learn common names for the first 5 aldehydes. I'll be straight up with you. The only way to learn those is to really memorize them. And if you're like, oh no, I got to learn, you know, something, I got to memorize something intense for chapter 13. Well, the good news is it's going to apply in the carboxylic acids chapter as well. So don't think that you're learning it and you won't be able to use it again. It will be very useful in this class. All right, let's get back to aldehydes. It says to name an aldehyde, you locate the parent compound. So we find the longest continuous carbon chain, but it's got to contain what? It's got to contain that carbonyl group from our aldehyde. We replace the E on the end of the parent with Al. That's it, okay? And also something interesting about aldehydes, since the carbonyl always has to be at the end because it's attached to a hydrogen on one side, it says you always count the carbonyl carbon as one, and you don't have to give it a locant, okay? And then you number and name the substituent. So if you have a 1-carbon hydrocarbon, right? And I'll just write one example out here. If you had a 1-carbon hydrocarbon, I don't know what that is, but you have methane, right? So you remove the E and the suffix is al, so you have methanal shown here. This is the IUPAC name or systematic name. Down at the bottom, this is the common name. You will be responsible for knowing those. So the common name of methanal is formaldehyde. I'm sure you've all heard of that. The next one is if we had ethane, then it becomes ethanal. The common name for that is acetaldehyde. Next, if you had propane, you drop the E, it becomes propanal. The common name from that is kind of a funny one. It's propionaldehyde, okay? Always a tricky one for students, but they always end up getting it in the end. And of course, if you had a 4-carbon aldehyde, so if we had 1, 2, 3, 4, like that, this would be butanal. And if you had a 5-carbon aldehyde, right, 1, 2, 3, 4, 5, this would be pentanal. Like that, so on and so forth, hexanal, heptanal, octanal, nonanal, decanal, undecanal, so on and so forth. Okie doke, let's move on from there. It says, how would you name this molecule right here? Well, the first thing you would do is you would find the longest carbon chain that what? Contains the carbonyl. And so that's this carbon chain right here. The carbonyl, we assume that carbon is going to be carbon number 1. And so since we have 5 carbons in the chain, we have pentane, we drop the E, it becomes pentanal, and then we have a methyl group at carbon number 2, and so this becomes 2-methyl pentanal. Okay, what if I put an example up here? Do you think you could name it? So what if I was to draw a molecule like this? Could you name this molecule? I'll give you a second to see if you can come up with a name for this molecule. And if you have one, just type it in. Who's the first? Yeah, Johnny, yeah, exactly. So I think you're definitely on the right track there, Johnny. So Johnny says, I'd start with carbon 1 here, 2, 3, 4, 5, 6, like that. So this must be some kind of hexanal. So this is a hexanal, and then we have a chlorine at carbon 5. So this is a 5-fluoro. A 5-chlorohexanal, like that. All right, there we go. Well, let's keep moving, and we'll look at more examples when we have more time. Common names of aldehydes, here we go. These names are taken from the Latin roots, as are the first 5 carboxylic acids. We use Greek letters instead of numbers to indicate the position of substituents. So after the carbonyl carbon, so after this carbon, after carbon, after this guy or this guy, then you go alpha, beta, gamma, delta. Okay, so alpha, beta, this is gamma, and then this is delta. All right. So since we have that methyl at the 2 position, this molecule becomes alpha methyl valoraldehyde. And if you're like, valoraldehyde, where did that come from? Hold on. look here. Here's the table of the first 5 aldehydes. So we go from methanol to ethanol to propanol to butanol to pentanol. Now those are all the IUPAC names. You are also responsible for knowing the common names. Okay, so you literally have to memorize all of these. Okay, so memorize. Okay, it's the only way, but you practice it enough, you'll get it down. So it goes formaldehyde, acetaldehyde, propionaldehyde, butyraldehyde, or butyraldehyde, and valoraldehyde. Valoraldehyde is kind of easy to remember because valoraldehyde starts with, looks like the Roman numeral 5 at the front. All right, anyhow, there we go. And if you're wondering, where do these words come from? Well, I could give you a lecture on that, but that's going to come up in the carboxylic acid chapter, because if you put oxygen in here to make all of these into carboxylic acids, you get formic acid, acetic acid, propionic acid, butyric acid, and valeric acid. And that's where these names originally come from. So I'll delete all that finish now. But that's something to look forward to in another chapter. Okay, it says here, examples of ketones. The simplest ketone has to have 3 carbons. You can't have any less than 3 carbons. Think about it. If a ketone has a carbonyl in between 2 R groups, and R groups have carbons, well, then you got to have at least 1, 2, 3. Okay, so the simplest possible ketone is this one shown right here, and this is called propanone, and the common name for this is acetone. Anyhow, let's go back up here. It says the simplest ketone has to have 3 carbons. To name it, we find the longest chain that has the carbonyl in it. We replace E with -one. So propanone, butanone, pentanone, hexanone, heptanone, octanone, decanone, so on and so forth. Nonanone. I skipped one, didn't I? Anyhow, indicate the position of the carbonyl by number on the chain so that the carbonyl has the lowest possible number. This rule here does not apply to these 2 compounds, propanone and butanone. It says right here, no number necessary. Why is that? Because it wouldn't matter where you put the carbonyl and butanone. If it was here or here, it's always going to be in the second position. All right, it's not until you get to 5 carbons that it matters. Let me prove it to you. Okay, if I have a 5 carbon ketone, if I have 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, if I put the carbonyl here, or if I put the carbonyl here, I get 2 different compounds. Right, my longest carbon chain in both cases, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You can see that in the first one, I have 2 pent and one, right? And here I have 3 pent and one. I'm going to draw another compound for you. I'm going to draw this compound one. And I want you to tell me what the name of this compound is that I just drew. Not a trick question. If you tell me the name of this compound. Yeah, Greg, like Greg says, it's 2-pentanone. Right? This is also 2-pentanone. I was just testing you to make sure that you wouldn't start numbering from the left and that you know it goes 1, 2, 3, 4, 5. And so these 2 compounds are the same. Those are both 2-pentanone. All right, well, with that in mind, let's take a look at this example. So this one is called 4-octanone. Why? Because the longest carbon chain has 8 carbons in it, and we give the carbonyl the lowest possible number, which is 4. So 4-octanone. And she even puts here not 5-octanone, right? She's giving you a big heads up. Don't make that mistake. Now, something else that I haven't mentioned yet are common names, and there are common names for ketone as well, ketones as well. And the good news is that they're actually a little bit simpler than the common names for aldehydes because there's not nearly as much memorization involved. You can see here the butanone. They also call it this methyl ethyl ketone. And here they call this butyl propyl ketone. You might be asking, like, how did they come up with those names? Okay. Well, they came up with them a couple of different ways. It seems like the first one for methyl ethyl ketone, they listed the R groups in order of size, going from small to large. Okay. And this is using size. And then here they used the alphabet because butyl is bigger than propyl, and they went in alphabetical order. So alphabetical order. Okay, and both of those ways are acceptable. All right, so let's go here. We already looked at an example for methyl 2-heptene. You know what? Let me just give you some examples and see if you can name them. So I'm going to draw a couple of molecules here. See if you can name both of those molecules. I'll give you a second to think about it. All right, I see that some people have started suggesting names. Let's give the first one a try, and we'll start by numbering the longest carbon chain. So 1, 2, 3, 4, 5, 6, like this. So this would be a hexane, but since we have a carbonyl, a carbon 2, this becomes a 2-hexanone. Okay, and then we have two groups at carbon 4. We have a 4-fluoro and we have a 4-chloro. Well, 4-chloro is going to come first because C comes before F in the alphabet. So we're going to have 4-fluoro. Move this guy. 4-chloro. 4-fluoro. And then we have our 2-hexanone like that. I see that a bunch of people got that one. Let's try the next one. Same rationale. We find the longest carbon chain, 1, 2, 3, 4, 5. We have 2 methyl groups on carbon 4, so this is going to be a 4,4 dimethyl 2-pentanone. Pentanone. Like that. So I see a bunch of people got that one too. Great. All right, perfect. All right, getting the hang of it, naming aldehydes, naming ketones. The trickiest part is that common names of aldehydes. But let's get back to that common names of ketones. This summarizes something that I just told you a few minutes ago. I said, based on the alkyl groups that are bonded to the carbonyl carbon, you can either do the alkyl groups either in alphabetical order. Either way is acceptable. You can do alphabetical order, or you can do from size going from small to large. Okay, the only thing you can't do is size going from large to small. Now the funny thing about these two rules, and the funny thing about why she includes both of these rules in the textbook, is that sometimes they give you the same name. Doesn't matter which rule you follow. I'll give you I think I have an example here. So if we look at this compound here, and I'm focusing on this guy right here, this is 2-pentanone, okay? 2-pentanone. Now the common name, you've got a methyl group and you've got a propyl group. So if you were to use size, you'd go methyl propyl, right? This works for size, and it does work for alphabetical. I'll just put A to Z like that. That also works. If you look at the next example, okay, this one's got how many carbons? 1, 2, 3, 4, 5, 6, 7, 8. So this would be 3. This technically would be 3-octanone. That would be the systematic name. You've got an ethyl group and you've got a pentyl group. And so you have ethyl pentyl ketone. Well, they both work. This one works for size and it also works for alphabetical order. I thought I had an example somewhere where they gave you different answers. I probably do somewhere. Anyhow, let's before we have to sign off because we got to get to the lab tonight. Let's talk about some important aldehydes and ketones. You've probably all heard of formaldehyde as a preservative used in the lab, maybe if you've taken a biology class. So I just want to point out that what they use as a preservative in biology classes is not pure formaldehyde, because formaldehyde is actually a gas, okay? So I'll draw in the structure of formaldehyde, which is the simplest possible aldehyde. It is actually a gas at room temperature, but when they bubble that gas through water, they make a solution called formalin, and that's what's used as a preservative. Okay, another one is acetaldehyde. So this is acetaldehyde. It's a 2-carbon aldehyde, also known as ethanol. It says it's produced from ethanol in the liver, causing hangover symptoms. So if you've ever had a hangover before, ethanol or acetaldehyde is one of the culprits. The next one is acetone or propanone. Here's the structure of acetone, and the reason that acetone is so important is not only it's a good solvent, but it's also used to clean glassware in the lab. Now, I know that we don't use it. We use soap and water in our labs. But if you ever work with compounds like sugars, for example, they're really gooey and sticky, and they're sometimes hard to remove from glassware. Acetone is really good at washing glassware. It's also miscible with water. And I want you to know that there's a difference between soluble and miscible. Miscible means mixable in all proportions. All proportions. That means you can put a little or a lot of acetone in water and it will always dissolve. It'll always make a solution. It's also flammable, so you want to be very careful when you're working with acetone. What's next? Important uses of carbonyl compounds. Well, this is something we could talk about literally all night. If you were to, start researching the structures of some prescription drugs, I'm sure you're going to find carbonyls from aldehydes or ketones found in many drugs, many medicines, many agricultural chemicals, and fragrances as well. In fact, tonight we looked at thiols and alcohols, but they're also used, or aldehydes and ketones are also used in fragrances. Here's some examples. You see this compound vanillin. So this is responsible for the odor of vanilla beans, a very pleasant odor. And what are the functional groups that we can see in vanillin? Well, I see that we have an aromatic ring. Right? We have an aromatic ring here. We also have what? We have an aldehyde. Okay, so we have an aldehyde. What else? Does anybody see any other functional group in there? I'll ask my students. Why am I doing all the work? Yeah. Johnny says an ether. Yeah, I agree. There's definitely an ether here. And somebody else says a hydroxyl. Yeah, so here's a hydroxyl from an alcohol. I'll put alcohol. If you put hydroxyl, that's totally fine. And then down below here, you have mushroom flavoring. If you're really into the flavor of mushrooms, well, now you know that it comes from this really simple compound, 2-octanone. And you can see that there's a ketone in there. Okay. What else do we have here? Benzaldehyde and cinnamaldehyde. So benzaldehyde is responsible for the odor of almonds. A lot of people like the smell of almonds. And so in benzaldehyde, we have an aromatic ring, and we have an aldehyde in it. Okay, and then over here we have aromatic. What about in cinnamaldehyde? Can anybody tell me what functional groups are in cinnamaldehyde? In cinnamaldehyde, does anybody see a functional group in there? Somebody says aldehyde, alkene, aromatic ring. Yeah, I think they're all there, right? We have aromatic. We have our aldehyde. That's given away by the suffix, isn't it? Cinnamaldehyde. And then here we have a good old alkene. Yeah. I just want to point out that Jessica mentioned that in vanillin, she said, well, isn't this a phenol? If you were to circle all of this like that, if you were to circle all that and call that a phenol, I'd give you 100% perfect. Yep, I'd call that a functional group. All right, some other interesting compounds here. It's the citral, which is the odor of lemongrass. You like the odor of lemongrass or maybe a lemongrass candle. You can see we have an aldehyde here. So aldehyde here. We also have an alkene, another alkene. So alkenes. And then we have Alpha demascone, which is some kind of berry flavoring. I think what's shown here is blueberries. Anyhow, you can see that we have 1, 2, 3. We have 3 alkenes in here. Alkenes, alkenes, and then we also have a ketone. And so functional groups are all around us, especially in foodstuffs and odors that we probably enjoy in our day-to-day lives. Well, that covers the first section of this chapter. In fact, this covers sections 1 through 3 of chapter 13.